Hi, everyone. My name is Kevin, and today I'll be talking to you guys about communication computation trade-offs in PIR. This is a joint work with many of my colleagues, both at Google and at Humboldt University in Berlin. All right, let's get started. So I'll first tell you guys what is private information retrieval, or PIR for short, and then I'll talk about our 3 contributions that we made in our paper. So let's start off with what is private information retrieval. It considers a very simple setting where you sort of have a user on the left and a server on the right that holds a list of, let's say, n data entries. And what the user wants to do is query for an index I and sort of receive the data entry at the ith index. So if you sort of do this in plain text without any sort of privacy guarantees, what happens is that the server is able to identify which index was downloaded. Excuse me. And over time, what happens is that the server is able to maybe view a large number of queries and get information about the user, and has been shown in practical situations that this can actually reveal information about the user or the user's intent. In an attempt to sort of solve this problem, private information retrieval was created or invented. And sort of the idea is, the user still wants to query for index I. It may do something more complicated that may include uploading a series of encryptions and then downloading a series of decryption of encrypted ciphertext and sort of decrypting locally to get the index VI. But it should be done in such a way that the server no longer knows what was the requested index. So it can no longer identify which index I was retrieved. And this is essentially what PIR tries to solve. So when you're trying to construct PIR, it turns out there are several efficiency considerations that you need to sort of balance. So the first one is communication. How much does the user upload to the server and download from the server? Secondly, there's also server computation. How much work does the server need to do when it receives these encryptions to create more encryptions or potentially decrypt and so forth? And simultaneously, there's also the client computation, which is sort of how much time it costs to sort of create the requests and then process the responses. So what usually happens is that communication computation, it's always a trade-off. You can never really, with the best constructions to date, either you can sort of play with these knobs and parameters that can either decrease computation at the cost of increasing communication or vice versa. And it sort of becomes this sort of game of trying to figure out what the best way, what is the best trade-off that we can achieve? And what we're doing in this work is providing many more tools that will allow designers or users to be able to construct the right PIR for their circumstance. So yeah, what is the best trade-off? And the answer is, there's never really a good answer. It really depends on the context. So for example, what we can typically guarantee is that client computation is more restricted. So you can imagine like mobile phones are querying a cloud storage provider. So client computation should be small. But between communication and server computation, it ends up being, it's unclear and it depends. And one way you can do this, for example, is to estimate the best trade-off using monetary costs. Like cloud computing services usually have prices for communication and computation, and you can try to compute this. And this is what we do in our paper. But sort of the point I wanted to get across is that it's never really clear what the best trade-off is. You can never say, you always want to drive down communication or you always want to drive down computation. It really depends on the setting. All right, so let's go into some a very simple example of a PIR scheme, which ends up being very important, is this homomorphic-based encryption of PIR. So at a high level, what happens is the user will encrypt homomorphically a sequence of n bits, which is essentially a selection vector, where all the bits are 0 except for the entry for which the user wants to retrieve will be a 1. So here, let's suppose you upload this selection vector, and then the server will simply use the homomorphism of the encryption to essentially compute the dot product. The first encrypted bit times B1, the second encrypted bit times 0, and so forth, and then sort of add them all together and return the result. And you can sort of see that as long as the user uploads the encryption correctly, the user will essentially download an encryption of the ith index that it wanted. But this requires sort of uploading n ciphertext. And there has been ideas to sort of decrease the cost of uploads in PIR. So an idea of this is recursion, where sort of you take the database and you sort of place it into a square in 2 dimensions. And now all the user has to do is upload 2 sets of square root vectors in encrypted versions, obviously, but in such a way that one set of vectors denotes which column the entry is in, and the other one denotes which row is in. And essentially, this would allow you to decrease the upload cost. All right, so with this sort of basic concepts out of the way, let's get to sort of the main results of our paper, our main contributions. So in our paper, we introduced something called MultPeer, which is a new peer construction. And what we do is we start off from a prior implementation of PIR called SealPeer by Angel, Chen, Lane, and Sethi in 2018. And what we're able to do is by implementing several optimizations, we're able to improve the upload by up to 75% and the download by up to 80%. So the communication, we've significantly decreased the communication. And this all comes in exchange for very minimal computational increases. So for example, if you're using monetary costs, this ends up being huge savings in monetary costs. So sort of achieve this new construction, we implemented 5 new optimizations. The first was, rather than using public key encryption on the client side as was done in the past, we end up using secret key encryption. And because we use secret key encryption, we can analyze the structure of the encryption and essentially replace a very long piece of randomness in the encryption with what happens, what amounts to be a very short PRG seed. Our third optimization was sort of when the server is going to send back downloaded ciphertext, rather than sending them back as is, what the server does essentially is it employs a technique called modular switching, which essentially compresses the download ciphertext before being sent back to the client. And this helps compress the download costs. Fourth, something I'll explain later, is an improved oblivious expansion algorithm. And then last but not least, our new construction is able to leverage multiplicative homomorphism, which was not done previously. So due to lack of time, I'm only going to explain the 2 bolded optimizations, but I do encourage everyone listening to go and look at the paper to see all 5 optimizations in detail. All right, so the first optimization ends up being not too complicated. So when you look at private key encryption or on the client side, it turns out that the encryptions are of the form C0, C1, which is a tuple, or essentially polynomials. But if you look specifically at C0, it turns out that C0 is really a uniformly random element independent of public and private keys. So one thing we could do is obviously the client could generate all of this randomness and send it to the server side. But in our work, what we do is we replace C0 with a very, very succinct description of a PRG seed S. So now with the PRG seed S, if either the client or the server wants to sort of generate C0 again, all it has to do is apply a PRG several times. And it turns out this is for example, a slight increase in computation, but it essentially halves the upload communication, ends up being very valuable and a huge optimization in our work. So this was the first optimization. It turns out to be very simple, but it's already very impactful as it reduced upload by half. So the other optimization I'm going to talk about is an improved algorithm for oblivious expansion. So in the work of SealPeer that we're building on top of, SealPeer had introduced this new notion of oblivious expansion. And what essentially means is that instead of having a single ciphertext per bit that's uploaded, you can encrypt multiple bits per ciphertext. So for example, let's take a look. Without oblivious expansion, if you wanted to encrypt this selection vector, you needed n ciphertexts. But with oblivious expansion, for example, it turns out that you could compress multiple bits into a single ciphertext. So for example, here in the example I said, maybe you only need 3 ciphertexts where you sort of fit n/3 of the bits into each ciphertext. And what happens is even if you use oblivious expansion, you compress this vector, the server will still be able to obliviously expand it back to the n ciphertext where each ciphertext contains 1 bit that's needed for example, the dot product. So okay, so this was a huge breakthrough. This is why SealPeer was able to actually achieve much better communication than prior works. But it turns out that SealPeer's oblivious expansion had some limitations. So one limitation was that the to be compressed bit vector, the input that's going to be compressed, had to have having weight at most 1. So this turns out to be a pretty big limitation in the context of recursion, for example. So remember recursion here with let's say 2 levels of recursion where we represent the database as a square, the client will have to upload 2 sets of vectors, 1 for the rows, 1 for the columns. And then each of these set of vectors has having weight 1 already. So because of this limitation of SealPeer's oblivious expansion, you needed to compress each of the bit vectors separately and have a ciphertext for each, because if you sort of concatenated them, the having weight becomes 2. So why is this so bad? Well, it turns out that there could be a lot of wasted space in the worst case. So for example, let's take a look here. What happens is you compress each of the set of vectors of having 1 into 2 different ciphertexts, but maybe only less than half of each ciphertext is being occupied and the other more than half are empty. So in our work, what we do is we actually present a new oblivious expansion algorithm without this limitation. So the 2B compressed bit vector can have arbitrary Hamming weight. We no longer care. And what happens is, especially with recursion, is that now we can compress all the uploaded bit vectors once. We can compress them once. We can concatenate the two in the recursion. Now there's Hamming weight 2, for example, we can still compress all at once. And the result essentially could be, in the best case, that they all fit into one ciphertext, and you have a lot less wasted space. And this all ends up improving communication. So how we came up with this algorithm is that we quickly noted that essentially the server oblivious expansion is linear in the plaintext space. So in fact, our algorithm not only works for bit vectors, but it can work for arbitrary vectors as well. So after implementing our 5 optimizations, we sort of did experimental evaluation and we present the results here. And what you can sort of see is that MALPIR is able to actually obtain much better results. So for example, if you look at the bolded parts, for 2 out of the 3 databases, MALPIR is able to obtain much lower monetary costs. And in general, MALPIR has lower download for a slight increase in upload and a slight increase for communication. But in general, it turns out to be better for monetary costs and a better trade-off in communication and computation. You should look at the paper for the full table if you need more, if you want to look at more details. So our second optimization was actually improving a different kind of peer called Gentry-Ramzan. So Gentry-Ramzan was a peer that actually was very, very optimized for communication, but had very high computations. And in our work, what we're able to do is present a new version of it that with tunable communication and computation trade-offs. So as a result, one of our instantiations of the tunable version of Gentry-Ramzan reduces the Gentry-Ramzan's server computation by up to 85%, but for an increase in communication sizes. So here's a table with some of these trade-offs, and you can sort of see the client-aided Gentry-Ramzan are essentially this tunable version that allows you to have higher communication, but lower server computation. And there's a lot to look in here, so I encourage everyone to look at the full paper for more details. Last but not least, our last contribution is a generic transportation from sparse peer to dense peer. So what is sparse peer? What is sparse peer? So essentially, sparse peer is sort of like dense peer, but rather than having each element be indexed from 1 to n, they're essentially a key value pair. So each entry is associated to a specific key, and the keys might come from a sparse universe. And what our work does essentially is presents a generic transformation where we essentially use cuckoo hashing to hash the keys and their associated values into 2 different tables, where each entry could appear in an entry in the first table or an entry in the second table. And then simply what we're able to do is now from sparse peer, you can just use 2 dense peer or normal peer queries, 1 to each table, to be able to do a sparse peer solution. Thanks for listening. And if you have any questions, feel free to reach out to any of the authors' emails on the paper for more questions. And thank you for listening.